University Graduate School of Business in 2021. Raghavendra's innovative contribution have earned him several accolades. He was the winner of Startup Pitch Contest at the India Startup Festival 2023 at Satyasai Grama, Mudenahalli, Bangalore. Additionally, he was recognized with the Top 50 CEO Award in the Emerging Leaders category at the Top CEO Summit in Bangalore during June 2023. His passion for innovation is evident in his intellectual property portfolio, which includes one granted Indian patent in the domain of low-speed aerodynamics and two patents filings in the agri-tech and aerospace sectors. As an active member of the entrepreneurial ecosystem, Raghavendra is an associate member of TIE, the Indus Entrepreneurs Bangalore chapter. Raghavendra's multifaceted journey as an engineer, entrepreneur, and researcher exemplifies his commitment to advancing technology and creating impactful solutions in aerospace and manufacturing industries. Over to Raghavendra, sir. Thank you. Sir. Are we audible?
Yes, sir. Good evening, Randall. I hope my audio is clear, right?
Yes, sir. It is clear. It is clear.
Yes, sir. So, first of all, thanks for the brief introduction. And I'd like to thank Dr. Vinayak Malik, sir, and the entire administration of KLS GIT College for giving me this opportunity. And I'd like to thank AICTE also, like in sponsoring such FDP programs, so which facilitates knowledge sharing and the networking opportunities for researchers as well as fellow academicians. So I hope, like yesterday, you had few insightful sessions actually regarding microwave processing. So today, actually, like we would like to give some information on 3D printing technology, that too into functional materials. Actually, we want to focus on. So I think I can share my screen, right?
Yes, sir.
Yes, sir. Please share.
So I hope you are able to see my screen now, sir.
Yes, sir. Yes, sir. We can see your screen.
Okay. So the topic like I want to discuss today is like 3D printing of functionally graded polymer matrix composites. So as sir was introducing, so currently I'm doing my doctoral work in metal matrix composite. So that is into like basically super inward composites, like we are trying to develop it, and that is specifically for a ISRO application. We are developing such composites, and we are doing material characterization, as well as we are trying to study the grain structure and how it can help improve the properties of the existing inward. So that we are exploring in our current work actually. But today, like I would like to give a brief on polymer matrix composites. So before proceeding, so I would like to start with a small introduction about our venture. So we are basically a team of aerospace engineers, and I started this company when I was doing my MTech by research at NITK Surathkal. So this was in 2018. So I started this as a proprietorship concern. So after a year actually, once my project was finished, so I incorporated this as a private limited company. So what we do here at Aakruthi3D is, so we provide comprehensive end-to-end engineering services basically for industries. So right from conceptual design till the production, actually, we have a dedicated team of resources as well as capabilities, you can tell. So we have dedicated design engineers, prototyping engineers, as well as we have in-house 3D printers, 3D scanners, as well as recently we established our subsidiary company, that is nothing but a manufacturing arm of our company, where even conventional machining, that is precision CNC turning and milling, actually we have been doing. So currently we are located at Pune industrial area. Our client base is more than 180 plus, actually, which includes Mercedes. We are registered vendor for Mercedes Benz Group, SKF, ITC, so and Magellan Aerospace, Unimec Aerospace, just to name a few leading OEM as well as tier one companies. Our team, we have successfully completed more than 500 projects, where more than 1,000 hours of design and reverse engineering expertise we have. We are also working some of the unique use cases in aerospace, oil and gas, like non-destructive testing, actually, you can call. So whatever the conventional method of aircraft inspection it is there, it is so much time taking. Using a pitot tube, it will take hours together of inspection. So if you want to inspect the surface of a wing, or like you want to inspect the body for any dent or any impact, actually, but with a 3D scanner, that is a laser metrology grade laser scanner, so it can be done in minutes of time. So that's the advantage or the unique value proposition which we are proposing to industries. And recently we are expanding to international market as well, so with these offerings. So some of our key products and services is, like you can see, as I told you, from conceptual design till the manufacturing, like we have the capabilities. And our vision is like we want to become India's own tech giant by developing and commercializing critical indigenous technologies in aerospace and defense sector, basically. So I can tell some of the R&D projects which we are currently working. So we are working on developing a metrology grade 3D scanning technology. We are working on indigenous 3D sand printing technology and a micro gas turbine technology. So these are three projects in our portfolio, where we are putting our dedicated efforts. And we have applied to even government grants, and recently we have raised an equity funding investment also from angel investors. So this is about us, actually. So what our team is working, and how I have been instrumental in doing these things. So coming to today's presentation, so I'd like to give a brief roadmap, actually, like what we are going to discuss. So we'll start with the introduction, then we'll have an overview of different 3D printing technologies. Then we'll go a little bit deep into polymer matrix composites and what are its applications, what are the future research prospects and challenges. And I'll tell you like how like I would like to address this session. So this is basically I'm trying to give you a review, actually, what are the research works happening in this domain. Because as you know, FDM, like almost like 10-15 years back itself, it became open source. Now everyone, they have got their hands on FDM 3D printers. So these consumer grade printers, like these Chinese made printers are their majority, they are overflowing the market. So everyone have got hands on it. It is basically used for low resolution prototypes, you can say. So that is the FDM technology. But if we are seriously thinking about applying it to some real world application, so that's where the composite material will come. Uh, for a typical application, maybe whatever the tensile strength or your mechanical property or electrical property, if it is not desired values, it is there. So then how do we enhance that property? So that is where the composite material comes into picture. And why 3D printing we are considering is, using 3D printing, any complex shapes can be created. So we want to take advantage of that complexity free technology, and then this we want to do the enhancement in properties. So that is where that both come together. That is the polymer matrix composite area comes into picture. So to start with, I hope like all of you are aware of the industrial revolution. So how it happened. So where it started actually, which started with the mechanization by powering by water and steam actually. From there we went to electrification. Then the automation came. Just 4 or 5 years back, actually, we were talking about Industry 4.0, where the IoT it was there, cloud technology, big data, all these buzzwords were hearing, and 3D scanning in which we are working also. That is also a part of this work actually, where we do digitization basically. So whatever your assets are there, maybe your complete civil structures are there, your engineering parts are there. So we are trying to replicate it in a digital ecosystem. So that is what Industry 4.0 it was all about. Now,
Sir, can you just click on that hide button at the bottom?
yes, sir.
Thank you.
Yeah. So now we are progressing into Industry 5.0. Like how uncertain the outside world is actually. Every day the technology is evolving. So earlier we used to say 5 years once the technology transformation happens, but today it is not like that. So whatever the chat GPT we were calling, it is like by revolutionizing so many fields, and it is going to take away so many jobs we were talking. But and recently US government also they had announced a $500 billion project actually, Stargate. So just by a few 2 3 days after that announcement, you saw Chinese that deep seek it came into the picture. Then that how they made it open source, how they made it so cost effective. So but this is how the outside world is actually. So every day there is evolution. So today one field whatever you are choosing, maybe tomorrow it is not relevant. So that is the way we are progressing, and the industry is evolving. So that is the Industry 5.2. So why I am telling this today is it is not just in the case of software. So it is in the case of our mechanical engineering field also, in terms of our manufacturing as well it is happening. So 10 years back what we were following, it is not the same. So people are looking at hybrid manufacturing. So even in manufacturing, like we are competing, we are trying to compete with China, but I don't know like when we'll be able to catch them in that race actually. It is not just in terms of the cost economics, but even in terms of the technology. So whatever they are producing at a fraction of cost, it is working very fine. Not just fine, actually, it is working better than the some advanced solutions in some cases. So that is the mindset or the research pursuit we have to keep. So the next Industry 5.0, it will be more on personalization and humanization. So one advantage of 3D printing, what I can say is it comes in mass customization. So till now we know only standardization. Standardization means you would take in terms of one example is if you go to buy a smartphone. For example, there is Samsung, there is Apple. So whatever the models they pitch to you, maybe Samsung Galaxy A9 or A10, in that range only we have to choose actually. Maybe like if I come up with some different specification which are not matching with those standard models, so there is no option, readily available option now. So that's the standardization. But with the 3D printing, what future we can envision is, so customized to your own application, your own requirement, your each and every features or the what the advantage you need. So that actually the OEM is able to give it actually. So that is the power of 3D printing. So in the context of Industry 5.2, so even that composite material also it will play an important role. So with this introduction, so I would like to go on to give you a overview of different 3D printing technologies. So this is one representative diagram where you can see different materials and the different compatible technologies of 3D printing. So there is polymerization actually, that is for plastic and wax, where the major technologies are like SLA, stereolithography, and digital light processing, DLP techniques are there. And the second technique is jetting, material or binder jetting. So that is also for it basically serves a range of materials like ceramic, metal, plastic, wax, and sand. And then you have powder bed fusion. So that is majorly for metal and ceramic it is used, but it can be used for plastic also. like SLS, SLM, like selective laser sintering, selective laser melting, and EBM. And there is deposition techniques, that is the regular extrusion techniques, as you can call fused deposition modeling, FDM, or its more open source name, that is triple F, fused filament fabrication. And for different for live cells there is 3D bioprinting, and for paper there is sheet lamination. So this is the technology landscape, you can call. For different compatible materials, there are different technologies. So, a brief overview, I would like to give some 3 or 4 technologies in today's session, where in the context of composite material, we'll see what are its advantages or disadvantages. So, FDM, as I started my session only, as I told you, so this is now available in every nook and corner of the market actually. So, it is most popular technique, and it is the most cheapest one, and it builds layer on layer by pouring melted filament onto the extruder. So you can see in the representation figure actually, there is a nozzle, and if thermoplastic filament like PLA or ABS, actually it is melted and it is go on deposited layer by layer, and there is movement in the build platform or the nozzle itself, it can move actually. So that is how your 3D object is created. So here, how do you control the quality of the parts? So there are parameters like layer thickness, it is there, and there is grid pattern, it is there, printing orientation, raster width, raster angle, and air gap. So these are some of the parameters which decides the quality of the final 3D printed part. So even after optimizing all these parameters, so I can say maybe like it won't give you a functionally working component actually. So that is one disadvantage of FDM. And one more thing is due to the thermal expansion actually of the polymer itself, whatever the final printed part we are getting, so there will be distortion in that. And based on the layer thickness, even there is compromise in surface finish. So we will have to go with different post processing techniques, like to increase the surface finish of this. Maybe like if you want some automotive surface finish or like injection molding finish, so that is not obtainable with FDM. So some of the commercial printers, like you might be aware of in FDM, or like Creality printers are there. Some high-end printers also are there, like Divide by Zero 3D printers are there, Stratasys printers are there. Maybe with the high-end FDM printers, we can come to maybe semi-functional parts, but not fully functional parts actually. So that is the drawback of FDM. And in composite metal context, what I can tell is, so whatever material you develop, so it has to be in a filament form to enable the extrusion. So that is one of the major drawback. And it is also difficult to homogeneously disperse these reinforcements and remove the void. So these two are the different challenges actually with the FDM 3D printer. So next one we'll see stereolithography. So this is in this technology basically resin materials we use. Why this technology is popular is there is great range of materials actually because of its material versatility. There are engineering grade resins like clear resin is the standard resin, durable resin, or your high temperature resin, elastic resin. And if you go to medical actually, so there are dental resins are there, or biocompatible resins are there. So due to its complete range of materials which can print actually, that material versatility, this SLA is popular. And one more thing is due to its surface finish. So you will get same injection molding finish in this SLA as printed condition itself. So that is the advantage of SLA. So coming to its physics, actually it uses photopolymers, so which will be cured by a UV laser. So the you can see the picture. So this is of a Formlabs 3D printer. So we have an in-house Formlabs Form 3B printer. So that works in this method. It is basically an upside down or the inverted SLA technique, where the build platform itself, build platform will be stationary, whereas this resin tank and that complete setup actually it will go down, and we will get the part actually in the inverted position. So here what we need to understand is what are the chemical reactions. So in FDM, we saw it is like a thermomechanical process. So whatever the heating and the melting process it is there, if that physics is followed, means like you can understand the internal structure actually. But here the chemical reactions that we need to understand during polymerization to control the quality of the final parts. So some of the parameters here which affects the surface finish of the parts is like intensity of laser power, scanning speed, and the duration of exposure. So this affects your curing time as well as the printing resolution. So here also there are post processing techniques. So once this part is ready, so it will be sent for washing and curing station. So in form lab ecosystem I want to talk, there are separate machines for this. There is form wash and form cure post processing machines are there, so which will do this work. So here like here also like how we can create a composite material is, so we can add directly to the resin itself, like photo initiators and UV absorbers you can add to the resin, so to control that polymerization reaction, what that curing reaction as I told. So the main advantage is you'll be able to print parts with very high resolution, and since this is a nozzle free technique, so there is no problem of nozzle clogging. So this is the advantage of SLA. And despite these advantages, there is high cost actually. Just to give an example of the current Formlabs ecosystem we are using itself, the resin itself will cost 24-25,000 actually per liter. So whatever trial and error we want to do means, so apart from your functional resin, you need to maintain the reservoir actually, even that should be filled. So to conduct an experiment, it is like two times the consumables you should be having. So that is how expensive that system is. And one more disadvantage is there might be possible cytotoxicity. There is some poisonous residues if it is there, if it is not cured actually. So that is also one major concern. And even in terms of handling also, like FDM, like it is a mechanical process itself, like you can easily operate. There is only the melting of that nozzle issues might be there. So all those things can be handled in a easy way. But here actually, since we are working with resin and the chemical reactions, so whatever you need to do, you need to be very careful actually while using these resins or different post processing techniques actually. So that is the disadvantage of SLA. And the next technique is SLS actually, that is selective laser sintering. So this here the form of material we are using is powder based processing technique. Same layer by layer process only. Here the grain size is around 20 to 30 micron grain size powder we are using. So this high power laser beam and the powder, so it will interact in a controlled environment. That controlled environment may be like inert gas environment we can use, and the powder fusion actually takes place for each layer. So you can see there is a roller, so which basically spreads each layer of the powdered material, and correspondingly the high power laser beam it is incident on the part. So how you do the slicing for FDM, so similarly here also that slicing happens. So wherever your part is there, that region itself the fusion takes place, and the remaining it won't take place. So and this complete piston operated platform it is there, so it goes on lowering actually for every step until your final product is ready. So what is the major advantage of this technique is this is a support free technique. So in FDM, like if you have worked, you might be fully troubled with the support removal actually. So wherever some feature are there, if it is mixed with support means, then it is very difficult to get that surface finish. Similarly in SLA also, so there will be minute marks actually. Wherever you remove that support structure, that mark will be permanent. Again, you have to paint it or you have to do some post processing technique to get rid of that. So but here it is not like that. So but there is no support. Whatever it is not the powder is fused, no, that itself it will act like a support structure. So here the feature resolution it is determined by different parameters like powder particle size, laser power, scan spinning, scan spacing, and scan speed. And there is one more parameter, a collective parameter you can call, that's an energy density. so which combines all these parameters. So based on the energy density, like you can decide actually like what is the behavior and how the part will come. And recently, like if you take powder bed fusion LPBF method, there have been efforts in numerical simulation of the itself. That is the complete build simulation. If you do so, you can predict the performance. So that is one thing I wanted to highlight here. So here the main advantages are high resolution and excellent quality. As I told you, it's a support free technique. Here the unbounded powder itself, it will act like a support. Some drawbacks are this is a time consuming process. Again, it is a very costly process. As I told you, in Formlabs ecosystem, you need to maintain a reservoir actually of your complete resin. So that is twice the consumables it was there. But here, the complete tank actually you have to maintain. That powder should be present actually. So that is still costlier than your SLA. And even after doing all these things, there are porosity issues. So even today, if you go and search research happening, there are so many researchers on how do you reduce this porosity, how do you reduce the crack formation, how do you make the grain structure actually very fine grain structure. So all this research it is still underway, and we have not still got a standardized parameters, or for each material there is no optimal parameters actually we can call. It's in SLA and FTM. So as you can see, the machine maker itself, they'll give the guidelines and they'll give so what should be the layer thickness, or what should be your infill density, all those guidelines. But in powder bed fusion, so it is not like that. So all the property printing parameters you only have to arrive by yourself. So if you change little bit powder composition also, so then the complete parameters you have to rework. And if you go on making trial and error, no, so this becomes too much costly process, and you cannot do it actually. It is not practically feasible. So there are many studies in optimizing these printing parameters itself. So even NASA is working on this, ISRO is working on this. If you can get a very printable, high performance super alloy, so that's a game changer actually for all the industries. Maybe today Tesla, it is what it is achieving today in space, or you can see our Apple, or any of these giant companies. It is because of these printable high performance super alloys only it is possible. So I think there is a great scope for research in this area. So now let's just compare actually what are the three techniques we discussed. So what are its advantages, disadvantages. So you can see, like as I told you, by FDM it's a low cost consumer machine, and the feature details also there is a low accuracy. It is there, limited design compatibility, and if you want to go for at least some semi functional components, there is high cost involved in that, and high performance materials are needed. So it is best suited for low cost rapid prototyping and basic proof of concept models. Only select end use parts with high end industrial machines and materials. And here the compatible materials are standard thermoplastic like ABS, PLA, and various blends on consumer level machines. And in SLA, there is great value you can get it because of its high accuracy, smooth surface finish, and a range of functional materials. So one disadvantage is so it is sensitive to long exposure to UV light, and some of the applications are like functional prototyping, like patterns, molds, tooling, dental applications, jewelry prototyping, casting can be done here. As I told in the starting itself, like there is a varieties of resins actually available: engineering grade resins, medical grade resins, casting resins, biocompatible resins. So but the list goes on. And SLS, finally, it is the superior of all three technologies, where you can actually create strong functional parts. There you have a great design freedom since it is support free technology. Only disadvantage here is the more expensive hardware, limited material options, and even in terms of software also, there is no open source software where you can do some trial and error like in FDM or SLS licenses you have. So such option is not available in SLS. So here the functionalities, like you can create functional prototypes, like short run bridge or custom manufacturing also you can do. Even batch production actually you can do with these SLS machines. Here the material compatibilities like engineering thermoplastic like PA11, PA12 and their composites, or like TPU, thermoplastic elastomers. So these are some of the materials which are compatible with SLS. So like one more about technology, like I want to give some briefing. So it is relevant to the composite printing technologies like 3D plotting or direct wire technique. So this is not so much popular technology, uh, but for composite, whoever has worked with composite, definitely they might have heard about this technique. So here this is the same like a extrusion principle, where you're extruding a viscous material from a pressurized syringe. This is in biocompatible material printing, like most popularly used method this is. So here you can see in the figure, so there is a syringe actually. So this syringe head actually it can move in 3 dimensions, whereas your platform it keeps stationary, where extruded materials are joined together layer by layer. So here also, like the chemical reactions or the curing reactions happens, it can be performed by dispensive to reactive components, so using mixing nozzles, or be induced either by heat or UV light. And here the quality of final printed parts is, one is like material viscosity and the deposition speed. So these are the two parameters which decides the quality of final parts. And one advantage is here also the material flexibility, that is in terms of like composites which you can do. So solutions can be printed, pastes, hydrogels. So all these forms actually it can be loaded into these 3D plotting printers. In today's in the context, this is relevant actually. So now we'll go a little bit in depth into the polymer matrix composite. So here I have listed some of the most popular techniques actually. Like one is particle reinforcement, second is fiber reinforcement, the third is nanomaterial reinforcement, and fourth is ceramic polymer composites. So we'll just go through some of the latest research happening in these 4 areas, and then we'll see some of its applications, and we'll try to figure out like what is the future trend, or like what exactly we can focus our research on like after this. So particle reinforced is the very basic one, and this is a easy method of preparing composites actually, because the particles are easy to be mixed with polymers, like either in powder form for SLS or in liquid form for SLA, and further it can be extruded into printable filaments actually. So here you can see the comparative summary table, where different 3D printing techniques are there, the compatible materials, and what is the resultant actually. The main reason why we are preparing these composites is we want to some enhancement in the property, like in mechanical property or in electrical property, thermal property. We want some enhancement as per a specific application, so that is our end goal. So with that in mind, so what are the particles we can reinforce, and whether it is 3D printable or not actually. So that is the crux of the discussion. So here you can see some of the classic examples are like you can improve the tensile or the storage modulus like by adding glass beads. So you can add iron or copper particles, or you can improve the wear resistance actually by adding aluminum and aluminum oxide. In terms of electrical actually, so you can improve the dielectric permittivity by adding ceramic particles or tungsten particles. So these are some of the standard particles actually you can call. And one more advantage here, what I can highlight is, so as I told, no, some of the disadvantages in the FDM printer, that is one is like because of that thermal expansion of polymer, your final part is distorted. So that is one disadvantage. And second disadvantage of FDM I highlighted is the parts are highly anisotropic. Like you won't be able to get an isotropic part there. So these two disadvantages of FDM we can overcome by reinforcing some particles actually. So but that is where we are going next step to the FDM, where particle reinforced polymer composites you can make functionally graded materials. So which was not earlier possible in FDM. One example is here you can see the first one, iron and copper particles. So if you add this, no, so it will solve your distortion problem in FDM. Why? Because in the latest research, it has been observed that by adding these particles with the ABS, actually specifically, there is a reduction in coefficient of thermal expansion. So thereby your thermal stability or the thermal distortion what it was there, so it is straight away removed actually. So that is one advantage. And second thing is here you can see thermoplastic elastomer slash ABS. Using that you can reduce the anisotropy of printed components. So if we can achieve this composition, I think you don't need to go for SLA or SLS itself. In FDM itself, we can prepare functional parts. So there is one more example of like aluminum and aluminum oxide. So it is fused with nylon 6. So this is used to reduce the frictional coefficient. The third example is like barium titanate with ABS and calcium titanate with polypropylene PP. So that can be used to improve the dielectric permittivity and controllable resonance frequency. And one more example is tungsten with polycarbonate. So all these examples tells you that so you can go beyond like thermoplastic. You can go one step next to the FDM by converting this into like advantageous technology. So similarly in SLA also, like earlier as I told you, directed to the resin itself, like you can add some particles like aluminum oxide slash UV cured resin. So here also there is improvement in dielectric permittivity, and similar for DLP. So while show some case examples after this, where you'll be still able to understand this. There are some magnetically assisted DLP process itself is developed. So we'll look at it in the coming slides, where how you can control the alignment of the whatever the particles you are reinforcing, so that you will get the like highly isotropic part actually. So that is the focus actually which we want to get. So this is one example you can see. So one of the researchers actually, this is I think in 2016 this study happened. So they have 3D printed a heat sink using the first picture, that A is acrylate resin, and the second one is the B you can see, that is a 30% by weight ratio actually, that composite material. So what is the particle they have added is like micro diamond particles in acrylate resin. So what is the enhancement they have got? You can see in the picture C and D. So if you both of the components, if you heat it in the similar temperature, that is for 10 minutes and 100 degrees Celsius, it's been heated. So you can see the difference actually here, 75, 57, 44, that gradient is there. But with the composite material, 82, 64 and 52 degrees Celsius, that is there is improved heat transfer rate actually by addition of diamond particles. So this is one classic example. So this is one more example actually, where your barium barium titanate actually. So that is actually infused with ABS polymer, and you can see the relative permittivity, how much change it is there. That is epsilon prime. With the normal structure, it was 2.57, and by adding 50% barium titanate, it has gone to 4.95. That is like almost double actually. And if you further explore the study, if this percentage is increased till 70%, then the property enhancement is almost 240% actually. So whatever we are telling, the property enhancement, everything, it is so much significant actually. So that is why this area is so much promising. And in the B example, you can see they have generated different structure like 1D, 2D, 3D periodic structures using the same composition. So this was the technique like I was talking in the previous slide, where one of the researchers, so he has done this novel 3D printing platform actually. It is a magnetically assisted 3D printing platform. Left side picture actually, that is picture A. where you can see you can create heterogeneous composites here. So some of the parts also it is mentioned here. You can see that green colored one, those are the dispensers, and the blue big one, so it looks like a nozzle, big nozzle, that's a mixing unit. And third one, the bed actually, that's a movable head deck. And the fourth is the table, and the fifth is the curing unit. And you can see a printed object with the internal helicoidal staircase, and we can see some of its optical microscope pictures as well. So main thing here we have to observe is void formation, actually how much we are able to reduce the void formation using this magnetic laser, because here when the 3D printing process is happening, so you apply a magnetic field so that whatever the particles you are adding, it gets aligned in the direction it is achieved. So that is one novel feature of this. So with this, I think we can go to fiber reinforcement actually. So earlier we discussed particle reinforcement. So this is also one more method where you can significantly enhance the properties of PMCs. So common 3D printing technologies in fiber reinforcement are like, one is FDM, and second thing is direct wire. That is like 3D plotter what we saw. So that is actually relevant for this fiber reinforcement. And here powder based techniques are not ideal actually for creating fiber reinforced, because you cannot create a smooth layer of powder and the fiber mixture, so that's difficult. So that's why that powder based technologies are ruled out. Only FDM and direct write techniques are there. And in FDM processing, so here the pellets and fibers, it are first those are mixed in a blender and then delivered to the extruder to be fabricated into filaments. And you can have a separate second extrusion process as well, to just to make sure that there is homogeneous distribution of fibers. And in direct writing processing, so there is a polymer paste and the fibers, they are mixed first and then directly extruded. So the technique is like this. So here you can see, obviously here also there is enhancement of properties you can call. uh, I think if you are aware of commercial printers, like I would like to give small overview here. There is Markforged printer actually, so which can print like some of the materials like onyx, so whose properties are equivalent to that of like aluminum itself. So that's a composite material which is having like, which is very lightweight actually, but which will give strength as that of an aluminum alloy. So such commercial based printers actually they are able to achieve this. But here the challenge is like there is short fiber and continuous fiber. Most of the research it is focused on the short fibers. So for example, you can see in the FTM technique, so the short glass fiber it is added to ABS, and short carbon fiber it is added to ABS. So and you can see the different loading percentage, like and how much the corresponding improvement it is there. So almost like 140% is the maximum improvement you can see. And even as low as 5% loading also, you are able to get some 24% improvement it is there. So similarly for direct wire actually, short carbon fiber and silicon carbide whisker and epoxy. So with the 35% weight, so 127% improvement it is there. And this is one more, you can see how much different it is there in terms of short fiber and the continuous carbon fiber. If you see the last column, the continuous carbon fiber slash nylon and continuous carbon fiber slash PLA, just 34.5% volume and 6.6% volume, you can see the improvement it is 335% and 446%. So that much improvement actually we are able to get with continuous carbon fiber. Again, as I'm telling, there are very few what you can call like commercially available printers which can print this CCF or continuous carbon fiber. And I don't know, like most of it not open source also. I think Markforged also it is not open source. So only when we develop a test bed actually like this, then we are able to experiment these methods. So otherwise, without a feasible test bed, I think whatever we are discussing, all the composite material, all these things, so there is no usage actually. If there is no test bed at all. So I think that is also one area we need to focus on. Like how do you make a test bed where you can experiment your different material compositions, you do the trial and error. For that one feasible test bed we need to find. Here, like I want to highlight one more point. So we saw actually that continuous carbon fiber, there is almost like 300-400% it is their improvement. But even then, like I think you will be knowing the rule of mixture we use for composite material. So whatever the theoretical value you get it by rule of mixture, so it is not matching with this 446% or 335%. It is still lower than that theoretical value itself. So but that is like experimental and theoretical values, what is the difference it is there. So here is one example where on the left hand side you can see the micrograph of the polished surface. Uh, what we need to observe is the void formation. Again, like if I quantify this, maybe around 10 to 20% void formation it is there. But if you look at the its performance, like tensile strength versus fiber loading, you can see it is compared with one more established technique, that is compression molding and FDM 3D printing. Both are compared. You can see the properties are like it is almost matching. So you can think like there is void formation, but still you are able to match that compression molding. So how is it possible? So it is only because like when you are doing the 3D printing itself, all those fibers, it gets aligned in your loading direction. So that is the basic reason why you are able to see the values closely matching FDM 3D printing and compression molding. So this is one more example actually, where you can see honeycomb structure. Basically, it's a bio-inspired structure. They're trying to print with fiber reinforcement, and you can see the progressive alignment of like high aspect ratio fillers with the nozzle during compositing deposition. As I previously told, no, like you can apply directly a magnetic field actually to control if there is any fillers which are magnetic in nature. So you can align them during the printing process itself. So this is also one such example like that. And you can see the material behavior, like engineering stress versus strain curve, it is there. For the pure resin, how it is there, and the longitudinal and transverse directions, and with this silicon carbide flakes actually filled with your resin, pure resin. So what is the difference in the behavior? Actually, it is directly evident in that picture. So this is one more method actually, like how we have a FDM. Only difference is here there is one more filament actually, it is getting fed to the nozzle. You can see the basic one is like filament supply coil is there, fiber supply coil is there. That is a continuous carbon fiber with the thermoplastic polymer. So those are getting combined in the extrusion head and then getting printed on the build platform. So this is how actually fiber reinforcement polymer composites we can print. So this is that one setup, and the second picture it shows the microstructures corresponding to that, and the third picture is the fracture pattern actually. So if that failure happens, so you can see like that fibers coming out actually, that pattern you can observe here. Now I think we can go to nano composites. So here the difference is, so we saw particle and fiber. Now we are adding nanomaterials actually, like carbon nanotube, graphene, graphite, ceramic, and metal nanoparticles. Here the challenge is like if you study about like graphene, it's a self-lubricating material. So how do you combine it with your regular polymers and you achieve that homogeneous dispersion? That's a challenge actually. So even my work actually it is concentrated on this itself. So we are trying to add graphene and graphene oxide actually, those two with the Invar composite. So we are using ball milling process basically to achieve that. But still, like how do you ensure that homogeneous dispersion, and how do you make that 3D printable? So those are the areas actually where we are working. Here also the main aim is you want to create some high performance functional composites or high performance super alloys basically. with the addition of nanomaterials. So you can see in FDM, SLA, DLP, and SLS. So what are the different materials it's been added, like carbon nanofiber. So similarly, like carbon fiber, continuous carbon fiber itself, like you saw how much difference it was there against the short fiber. Now you are adding carbon nanofiber with the ABS. So there is still more improvement in terms of tensile modulus strength and the reduced elongation it is there. And if you add again graphene with ABS, so you observe an improvement in electrical conductivity, thermal stability. And if you add that with polystyrene, like carbon nanofiber or graphite with polystyrene, so you get better voltammetric characteristics. So this is in terms of electronics actually, like whether you can print uh, whether you can print functional electronic components, like uh, that is the area actually where all these examples will come. So similarly in terms of SLA, you can see some photopolymer, it is added with CNT, graphene oxide, uh, and acrylic exter and CNT, where you can get improved piezoelectric coefficient, tensile strength, modulus, flexural strength. Similarly in DLP and the SLS actually. So this is one example actually. You can see how this method works or how you can prepare that composite. So in the picture you can see the first one is graphite flakes. So how it looks, and B and C are like if you disperse graphene oxide and ABS in a solvent. So here the solvent used is N-methyl pyrrolidine. So how that solution looks actually in B and C you can see, and in D and E, so you create that homogeneous mixture where graphene oxide ABS in NMP before and after that chemical reaction actually you can see that, and the F is the one where graphene ABS coagulations obtained after isolation with water, and finally if you wash and dry that you will get that composite powder. And similar to FDM process itself, here also it is followed. You can see the bottom left diagram where you can see that 80-degree build temperature it is there. Only issue here is there is frequent nozzle clogging issue it is there. So whatever the composite material we are trying to prepare, if the nozzle gets clogged again, like you have to remove it, you have to clean it. Maybe like different nozzle sizes we have to change, like 0.4, 0.6, 0.8, 1 mm or 1.2 mm. This trial and error actually it needs to be done, and the final output you can see in the picture I, where a typical 3D printed model using 3.8% actually graphene is used with ABS here to finally achieve that output. So this is one more example where nylon actually like PA11. So it is combined with silica nanoparticles, and you can see different compositions have been tried: 2%, 4%, 6%, and 10%. And finally, you are preparing a gripper where it is a functional gripper actually. It is not just aesthetically. So you are able to replicate that exactly versus the pure nylon. What is that improvement they have studied in this study? So the last example is like the ceramic polymer composites. So again, here also ceramics, there are we can add many ceramic particles actually for both which are compatible to like FDM, SLA techniques, or there are some special techniques like special technologies itself. They are developed for ceramics polymer composites. Since like I don't have much exposure in the ceramics, so I thought like I'll just give this comparison. So now we can go to some of the applications of PMCs. So where it can actually benefits. So this is where it gets interesting. So whatever we are seeing now, like maybe in movies or like wherever the fictional part of 3D printing is involved, like you can print some complete human body itself, or you can print cells, you can print textures like tissues. So all this comes in this application part, or you can print complete the drone electronics. Imagine like now you are printing the drone body, but inside the electronics also, if you can print it during that process itself, that's a structural electronics I'm talking about. Then I think there's no limit actually. So much potential it holds. So those all applications actually I think we can see in this slides. So the first thing is like aerospace and automotive. Like as I was telling about the drone case itself. So here you can see two profiles. Those are basically blade profile and propeller airfoil profile, and using glass fiber composite and carbon fiber composite. So just a cross section to establish the feasibility of printing, you can say. So you can see in this that C, D, G, and H. So these are glass fiber 3D printed models, and E, F, I, J are the polymer composite printed models. So this, as per your build volume, or as per how big you want, you can print it, or as per your application, you can customize this. So coming to biomedical application, so you can see biomedical means there are some naturally derived polymers are there. So that is standard used, like gelatin is there, alginate is there, collagen is there. So and there is synthetic polymers also, that is PEG. So PEG is polyethylene glycol, and PLG, that is how PLA we use. Similarly here, like polylactic chlorglycolic acid it is called, and PVA, that is polyvinyl alcohol. So these materials are the synthetic polymers. But in biofabrication, so you can see the internal microstructure, how uniform or the crystalline structure we are able to obtain using this. And PLA slash PEG and PLA PEG and G5 scaffolds, you can see the fluorescence images. The scaffold functionality is, so inside microstructure we need to replicate here. So once that is done means the functionality it is taken care of. So that is what we are trying to look at here. And this is one example of a bionic ear, where you can actually print cells, tissues. There is recently 3D printed heart also, you might have heard. But it's a functional heart actually. It is not like a replica or something. Even medical models using binder jet, you might have seen. That is maybe 5-10 years back we used to see those. That is used to train the doctors as mock models, actually mock anatomical models. Now if you can print actual heart itself, it's a functional heart. So then you can imagine like how much big problems are there, like in terms of transplant, heart transplant, or in terms of organ transplant. So many areas actually it can be overcome using these applications. So in the image you can see the first AI image, it shows the CAD drawing. So obviously you need to start with the design, then the comes the what are the materials you are going to use. So material means there is biological component, there is structural component, there is electronic component. So this is where like what are the different technologies we serve for different materials. Here you can see a multi-material approach and multi-technology approach as well. So to make a functional ear, you need obviously like biological component, that is chondrocytes they have used here, and the structural component is the silicon, and it is embedded using like the electronic component, that is AGNP infused silicon, to form this bionic ear. Finally, final image you can see the what is the 3D printer used for this printing, and the 3D printed bionic ear. And they have even observed there is tissue generation actually. So how it happens in a regular human ear, so that has been observed here. So that is the extent of like technology advancement you can call till now. So this is in electronic applications. So the 3D printed carbon black slash PCL composite for like piezo resistive sensors, capacitive sensors, and the macro image of printed sensor pads actually you can see here, where it is not just the structural component. Maybe like you want to embed the functionality in that structure itself. Whether it is this can be explored is one application of electronics. So I can give one example where nowadays you can see like if you're launching the satellite and all, there is so much structural weight. It is the dead weight actually, which forms the majority of the payload. But what if you can, instead of deploying separate solar panels or anything like that, in the body itself, if you can integrate some form of energy storage on the energy conversion device. So that will reduce so much of your dead weight. There's no need for carrying your batteries or anything. So that is one application. Only using 3D printable, uh, what you call the functional structural electronic parts, you can explore. And there is one more significant area actually. So there is research going on is like 3D printed solid state batteries. So the current batteries, how it is operating and how it is outside environmental factor it affects, like so many electric vehicle accident you might have seen actually. Why? Because whatever the conditions in western, actually they replicated that exact design here. That ambient condition and this year ambient condition is different. That's why that so many electric bike explosion and all you might have seen. But instead of that, if you can make a 3D printed solid state battery, imagine you don't need a battery compartment itself. Your maybe electric vehicle inside that body itself, if you can embed that functionality where the possibilities are endless actually. So that is one area, like I think like I want all of you to look at that. There is one American company, I'm not able to recall that name now. So they have done a proof of concept on this. So a functional 3D printed solid state battery, you can find it out. So this is the future we are going towards. So in the industry 5.0 where I started, so this is where actually it is getting connected. So we are going to a future where all the fields, all the technologies, it is merging to make a better future, like in terms of aerospace, automotive, biomedical, electronics. Because of advancement in these applications, so we are like we're the kind of reverse engineer, like we need to work on the material, we need to work on the feasible technologies for that. So that is how, even as I told you, it not just in software, that is in artificial intelligence or big data, even in mechanical and hardware, because finally it is supported by both are correlated actually. So we also need to go in that path. So this is one example of preparing the structured electronics, as I call. So you can see one part of electric circuit, it is printed from emulsion of 70% weight ratio, like dipropyl glycol diacrylate as oil phase, and it is then uh, what you call it, it is immersed in one of the oil phase, where they are trying to kind of like a shape memory alloy, they are trying to replicate in electronics field, where the printed structure, it is embedded with the silver nanoparticles. So can we generate the electricity, the electron movements actually when 3D printing? So this is one area where they are focused. So I think with this, I hope like you got a fair idea of what are the different PMCs actually, areas research is happening, and what are its different applications. And now I think we can talk on what are the research prospects and the challenges. So this is where relevant to our fields, like we need to introspect, and we need to come up with what are the research focus areas we can think about, and we can come up with some project plan or something tangible to contribute in these areas. I think we can explore this. So, as we told you, there are recent developments in additive manufacturing. So, they have enabled researchers to produce products with customized and better mechanical properties. So, it is basically due to the demand from the industry side, that is from aerospace, from biomedical, from electronics, from semiconductors. Because of this, we are looking at this angle of producing high strength and lightweight products. So because of this, the PMCs, they consume much attention to the modern world. So these products possess brilliant mechanical properties, durability, as well as other thermoelectrical properties. So however, the disadvantage here is, so the addition of fillers, it is limited to a specific amount. So that is called a threshold point. So after that, the filler particles, it start making the and it increase the void formation that leads to the reduction of mechanical properties. So sometimes these physical properties are the particle size. They don't allow the printers to extrude properly, and they reduce the bonding forces between the two material. So that will again promote void formation and it will affect the surface finish of the product. So I think whenever we develop a composite material, so this is what we need to take care of. So that is like how do you reduce this void formation, and how do you make that interfacial bonding, actually that strong bonding, how do you create? So if we take care of these two, then automatically we can achieve whatever the desired properties which we are targeting for any specific applications. So these 2 points like we need to work on, and these following limitations you can see, so which need to be overcome by I'm giving like 3 P's we are basically here. So the first P is printable materials. So as I told you, like uh, all the big aerospace companies, automotive companies, they are on lookout for this. So they want some high performance printable super alloy. So there are like the standard methodologies also, like alloy by design methodology, it is there. If you can come up with such compositions where it is 3D printable, where you can get the optimum printing parameters are set, no? So then like all industries, they welcome this move and it will be a game changer. So we need to work on synthesizing these matrix material with special properties, with new enforcement, with new mixing composition. This is critical to increase the versatility of composites printing technology. And one more area we want to see is like in terms of sustainability. As you know, like 3D printing, it is aligned with our SDG goals, because we are reducing the like environmental footprint. And since we are working on a in principle it's a zero wastage process, actually, since it's a toolless process, so it's a zero wastage process, so that it aligns with the sustainability development goals. So we need to develop such more sustainable materials to reduce material cost and environmental impact. And the second piece, performance. So how do you eliminate the formation of void during printing, and how do you ensure good interfacial bonding between matrix and reinforcement? So this requires further significant research. And moreover, the repeatability and consistency of manufactured parts cannot be guaranteed by printing. So this approach is to ensure the uniform properties of printed parts need to be investigated in depth. So like since my last 5 years experience in this 3D printing, so this point I can more confidently I can tell you this, because in aerospace and automotive, the main challenges is in terms of certification, in terms of qualification. So all our like HL, NL, or ISRO is there. So they're all ready to welcome this technology. Only thing is the parts, they are not qualified as per the standards or the regulatory what you call the regulatory norms are there, so it is not able to pass that. Why? Because you are not able to get that repeatability and consistency of your manufactured parts. I think that area it needs a subsequent amount of research, actually, where this will facilitate further implementation across the application. So whatever the applications we are telling now, maybe it is only in prototype stage or limited batch production stage we might be talking. But in terms of making it a mass technology, like how you have CNC and all, similarly, like if you want to make it a mass adoption technology means, so I think this area it needs to be more research, it is needed. And third P is printing technique. So as I told you, there are no like open source test beds, actually, or maybe there are very limited test beds. So whoever the industry player is there, so for them this consumable is a very big market, and the after sales market is a very big market, more than the machine sales they earn from this. So that is where they are inhibiting in one way, actually, like they are inhibiting this adoption, you can tell. So there is need to develop new printing techniques. It should be based on like scalable and fast processing of materials. It needs to be developed. And one more disadvantage, maybe whoever has worked with basic, even FDM 3D printers, you might be knowing. If suddenly power goes, or if there is some parameters, the machine got stop or something like that, the printing gets halted there itself. And again, like you need to start from scratch, actually. Again, you have to start loading the material, you need to start working on that. So such what do you call that, fail-safe feature actually we need to work on, where there should be a feedback system. It should be built in the 3D printer to have a response to the process change. For example, in terms of long prints, I think you might have observed in FDM, if it is maybe some 50-hour print, 100-hour long print, if there is one small error, one layer it is not coming proper, means it will go on continuously. The process remains same. There is no, if that layer is come properly or not, there is no feedback system actually. It is built in the printer to have that response. So now we are developing like artificially intelligent systems. I think similar to the machine also it needs to be built. So whatever the deposition it is making, whatever like even in photopolymerization, so whatever the photopolymeric reaction it is happening, there should be some intelligent system or some feedback system where that in situ monitoring should happen. Like if there is a defect found in layer one, means okay, like correspondingly the machine behavior should change, so that actually next layer it is not propagated. So that is where I think there is significant research it can happen on the feedback system built in into the 3D printer. So with this, I think these are the three P's where we can introspect, like what are the currently we are working on, and what are the available resources with us to come up with better printable materials, better performance, and better 3D printing self-aware, or like what do you call, in situ monitoring systems to further enhance this field. So these are some of the major sources actually I have referred. So I can share this also, like after this session. So I think if you have any questions or anything, I think we can discuss on this. Hello.
Hello, sir. Yeah, thank you, Raghavendra sir. It was a very wonderful session. As most of us only worked on FDM, not on the other type of 3D printers. It was really an eye-opening to us. And also, I would like to ask the participants if they have any questions.
We remove we will remove the restriction now. Or they can unmute and ask.
So just a minute. Yeah, now it is open for the audience. Audience can ask questions. We have unmuted the audience as well. So if anyone is having any questions, you can ask. Sir, there is one question in chat box by Vishnu Pant Misale. Shall I read it?
Yes, sir. Actually, so I'm looking at it. I want to know more about.
Yeah, Vishnu Pant, you can talk. Not a problem.
So I think one question is that FDM technology, it is very commonly used for prototypes. Is it possible to use FDM in structural or functional application? So this is where actually that particle reinforcement I spoke about. So we all have access to FDM 3D printers basically. But what we can do more than the normal prototypes or the low resolution prototypes, that is where this field gets interesting, where you can add some particle reinforcement. You take normal PLA ABS pellets itself, you try to extrude, you try to add this material, as I told, no, for the FDM. So you can add like iron particles, you can add copper particles. Using that, there is a reduction in coefficient of thermal expansion. So there is no thermal distortion from your FDM parts, that is removed. And if you add TP actually, so that is thermoplastic elastomer, so that will reduce your anisotropy. So whatever these two are the biggest drawbacks of FDM, it is there. So if you can take care of that using this composite material, right? So I think even FDM also it will be same treated as like your LPBF or SLS technique. So I think this answers that question. So can we manufacture continuous carbon fibers, carbon particles, and carbon too, and their prospects? Definitely, sir. Actually, we can manufacture. So the CNT, graphene oxide. So all these materials are available. I think you can do that. Only thing is, as I told, no. So whatever the properties we are getting, so it doesn't match with your theoretical values. Why it doesn't match is the lack of homogeneous dispersion, you can call. So even if you approach some of the OEMs, no, so I don't know how many of them will be able to give you that homogeneous mixture. So that is the challenge actually. So as I told, that graphene, it's a self lubricating material. So how do you mix that to make it that uniform powder, which should be 3D printable? So finally, you will come up with some material. If it is not 3D printable, it doesn't serve the purpose. So that is the challenge actually. So but I think if we can start somewhere, actually, if we can start small, no, so then we can achieve the 3D printability, and we can achieve the functionality also. I hope this answers your question, sir.
Vishnupan sir, Vishnupan sir, Vishnupan Misale sir. Yeah. Any other questions by the participants? Okay. So if no questions, then we are going to close the session. Thank you, Raghavendra sir, for that insightful talk on 3D printing. Thank you, sir.
Yes, sir. Actually, thanks for the opportunity, sir. So I think like most of the audience were related to research only, I feel, because whatever I told, it was like kind of a review of researches happening in these areas. So if we can inculcate some one or two aspects in our regular research area, no, so I think that's the usefulness of the session, I feel. And if there are any further questions, or maybe if you need help preparing some composite material or some 3D printing aspect of it, I think we are ready to help in that aspect as well. So I think let's take this as an initiation rather than closing this session. I think it should initiate further avenues of research as well as collaboration, I feel actually. Thanks once again for the opportunity, sir.
Yes, sir. Sir, I think there is again one question from Vishnupan Misale sir.
Okay.
Am I audible, Vishnupan sir?
Kindly unmute, sir.
Yeah.
Are you able to hear me?
Yeah. We can hear you.
Sir, it's an excellent lecture. I was very much fascinated to listen to your lecture. So, number one is that you talked about the reducing the coefficient of expansion in the case of inward. Normally, in aerospace materials, we use the inward material for the cameras, and
Yeah.
they are normally very heavy. So, by reducing this coefficient of expansion, we may be able to use new material to reduce the weight. So we should be able to understand exactly how much reduction in coefficient of expansion we can achieve, and with reference to the current materials like Invar, by adding the additional substances. So any work is being done on that.
Yes, sir. Actually, like we are developing a super inward composite
Yes.
where normally, like if there is 1.8 ppm, it is there your coefficient of thermal expansion.
Yes.
For your super inward, it will be in the range of 0.4 to 0.6.
Oh, that is excellent, sir. So
Yeah.
now you were talking about in aerospace materials, they will not use and all. They will definitely use it, provided the properties are accurately measurable.
Yeah, that is correct, sir. And there is one more problem, no, that part qualification should happen. That is
Yes,
where
sir.
the certification authorities will come.
Yeah. That is for that purpose only. We have to give the data that yes, exactly it meets this much properties. You will get like that.
Yeah.
So
That's what,
that
sir. Like more work actually it needs to happen. Like more and more databases get created, no. So
yeah.
that will create a confidence in the industry.
So who will be manufacturing this, or who will be able to do this, or give us the material? We can have some interaction.
I think, sir, if there is specific this one, no, like I have a network actually. So
Okay.
if you are looking
So
for
what?
some specific this one, I think we can connect after this. I can get in touch with you.
Great, sir. We will connect. No issue. That
Yes.
is one thing. Then second is this the property reduction. What was the thing? My base question was when we're adding the different materials, how is the bonding between these materials and the resin works? Whether they will bond properly or no. About that only point of discussion will come, and then we will find something called resin rich, resin lean areas and all. So about that, some work should be done. And what should be the these fibers? Basically, when you asked about carbon fibers, what should be the size of the fibers, etc., whether they are all defined well, is also one question, sir.
Yes, sir. Yes, sir. Actually, so we need to explore, sir. Actually, like even we have started our work recently,
Yeah.
and from the manufacturer also there is very limited guidance. It is available.
So I was thinking whether any startup can form to understand this phenomena.
And definitely, sir. Actually, because now there is huge push for like deep tech in the
Yes.
country.
Yes, sir.
Yeah. So recently in the budget also you might have seen that fund of funds they have announced for deep tech companies.
So basically, this thing was to understand the carbon fibers and the base resin in which we are going to put this particular thing, how
Okay.
the carbon fiber will interact with those things in the molecular level or the atomic level, like that. Whether so that if we can ensure or test some bonding between this carbon fiber, one single carbon fiber and its neighborhood, so what is the percentage of bonding or something like that, and then we can generate it for entire substance. So if we are able to generate the data for the entire substance, then it is possible to use these materials in aerospace
Yes, sir.
applications.
Yes, sir. That's what, sir. Actually, that is where actually like we need to understand the chemistry also. So
Yeah,
this
yeah.
is since
Yes.
we are working from the engineering background, right? So
Okay.
we are more aware about the applications and real time problems. But
Yeah.
the fundamental that material research should happen actually from science
Actually,
perspective.
material research does take a lot of time because we know to make one maraging steel substance, we took a lot of time in ISRO.
Yeah, yeah, yeah.
Okay, so similarly, if the material now we cannot change that material so easily unless proved otherwise that other material is better than this. So same
Correct.
fashion, I was thinking in the case of the satellites where we use the cameras in different types of cameras, the material will be very heavy.
Yeah.
That is inward based material only, but it will be very heavy. And if we by reducing some weight by additives or and also if the properties are going to be improved, we must do the research on that area, sir.
Yes, sir. Yes, sir. Definitely, sir. Because this Invar only, no, in
Ah,
1920 Nobel Prize it was awarded to Invar.
yeah,
So
because it's
now you can see like more than 100 years actually. Still we
yeah.
are talking about 3D printability of it or manufacturing of that.
Sir, where do you work? Actually, I don't know. I'd like to meet you.
Definitely, sir. Actually, like
Okay.
um,
Okay. I'll interact little later.
sure,
And
sir.
then I'm into vnmisale@yahoo.com.
Okay,
You can send me this one, sir. Huh?
definitely, sir. Definitely, we'll
We'll,
connect
we'll,
after the
okay.
session.
Thank you very much for the wonderful FTP program you have developed.
Yes, sir. Actually, thank
Yes,
you,
sir.
sir.
Bye.
Thanks for the opportunity, sir.
Yeah.
Hi, sir. Good evening.
Yes, sir. Thank you.
Yeah, good evening,
This is
sir.
Srinivas Raghavendra, sir. Overall, it's a very good presentation, sir.
Yes, sir. Thank you, sir.
Sir, the thing is, what are the composites you have tried, and what are the ASTM standards as of now you guys are following, sir?
Sir, actually, like I am working on the metal matrix composite, as I told you in Invar. So
Okay, okay,
there we have just started with like as I told you, know that graphene blending. So
okay.
we are having challenge in that. So and we are taking help of a company called FNZ Minerals. So
FNG.
yeah, FNZ.
Okay,
So they are doing that ball milling process and they are trying to get that. But
okay,
still, we are just trying to add like 0.5 to 1% we are trying to add. But
okay.
that itself, it is creating a huge challenge actually.
Mm-hmm.
So we are in that phase now.
Okay, okay.
So, and we are taking the help of like NIT Trichy also in this.
Tiruchi.
Yeah, yeah, yeah. and that's all, sir. But now only recently, like we have started this work, and
Nice, sir.
yeah. Like previous example, I can tell is like we have worked with onyx material, so that is from Mark Forged technology.
Okay.
So that readily you can print actually, but it's not a open source printer, and material cost is also high.
Okay.
Yeah, but you can get the property same as aluminum, like 6061 or something like that.
Okay.
Yeah.
Like suppose for example, I can go like for example, I can come to the FDM side. We can no, make it into composites, and we can make the filament making facilities available, sir.
Like it is with one of our vendors, sir. Actually, like we are directly giving 3D printing service of like existing materials.
Okay, existing materials.
Yeah. Composite, it comes to again like R&D kind of phase.
Yeah, correct.
Yeah, and we are using that Formlabs, all these machines now. So these are
Okay.
not open source actually.
Right.
Yeah. So, but if required, like we can get it done, sir. Actually.
Sure, sir. I'll get connected with you.
Sure, sir. Sure. Thank you.
Okay. Thank you, sir. Thank you so much.
Yeah.
Sir, any other questions?
I have one question, sir.
Yeah.
Sir, you in one of your slides you have shown some gradation of some materials. So my question is it possible that gradation with metal and ceramic both?
Okay. This is which one you are telling, sir?
One of your slide you have shown some properties are changing across the across the height.
Okay, that heat sink example.
Yes.
Yes,
So
sir.
such type of printing is possible with metal and ceramic.
Yes, sir. Actually, it is definitely possible, sir. Only
Is
thing that composition we need to achieve, no?
that...
So how much percentage that homogeneous dispersion? So if we take care of those two, then printability we can achieve.
Okay.
Yeah.
So in that facility is available in India.
There are available facilities, sir, but limited you can tell.
Okay.
Yeah.
Okay. Do you know any of such facilities then?
That's what, sir. I told about that FNZ. So we are working with them. So similarly, like 2-3 other players are there,
Okay.
which can do that actually. So if you tell specifically which material or which one, this one, no, I think I can connect you.
Okay.
Yeah.
All right, sir. Yeah. Then I will connect you with you later.
Okay, sir. Okay, definitely, sir.
Thank you very much.
Yeah.
Any more questions? Yeah. If no questions, then we will end the session number 3 here. We'll be having a 10 minutes bio break. So we request all of you to join by 7:35. It is 7:25 now. You can take a break of 10 minutes. Next talk will be on the 3D printing of functionally graded materials of metal matrix composites actually by Samyak sir. So please join us at 7:35. Thank you.
Thank you, sir.
7:50. What is the time, sir?
7:35. 7:35.
Okay, fine, sir. Thank you.
Thank you.